Hello there, math fans. I have several things I would like to do related to circular motion, and I realized that before I did that I should give a little primer, and that way I don't have to give an explanation in the other videos themselves. I have a video about merry-go-rounds, I have a video about spirographs, several different things I'd like to do, but they all require a little bit of understanding of circular motion. For my students, if you're going into Math 126, circular motion appears a lot. So this will be helpful for you there. And let me just give a brief visual of what I mean. So if we set this thing in motion, here's circular motion. It's something traveling at a constant speed around the unit circle. Knowing the equations for that is very important. It's also just fun to be able to make such pictures, but here we have it traveling counterclockwise. When you get to 3D, you do similar things. So in Calculus 3, we do 3D, and it's the same setup. Here I'm just drawing a circle on the ground, if you can see that. And it turns out we often have the other variable doing something else. It could be a little higher, like 3 units higher, like this. It doesn't change the circular motion piece. You can even have that changing. Like you could have it increasing and then spiraling up. And those are some key examples we use a lot in Math 126. They all require an understanding of circular motion. I find a lot of students don't know this, that standard circular motion is counterclockwise and what the equations are, so this will help with that. Okay, so I'm going to step back a little bit just to make sure we're clear here. Trig starts here. It starts with a right triangle and an observation that if you have the 3 sides of the right triangle, it doesn't matter how big or small you make that triangle. If it's a right triangle and has the same angle here, then the ratios are the same. And that's where trig starts. And somebody said, well, let's give a name to those 6 ratios and store them, because it can be useful if you know 2 sides to then know the ratio, and by that you find the third. So actually, if you know 2 sides, you can do Pythagorean's theorem. But if you know 1 side and the angle, being able to figure, like if you know the shadow of a tall tree, you probably won't be able to measure how tall the tree is, but if you can measure the angle to the top of the tree, even just knowing the shadow of the tree, and you know where the sun is, you might know that angle. So it's useful when working with triangles. So there are 6 names, and I'm not going to spend much time here, but I just needed to say this. There's sine of, because it's something I get asked a lot. They're like, why does this come up in circular motion? So I'm going to just take one step back, and we'll be there in just a moment. So you get these definitions. SOHCAHTOA. I didn't know that till I was a student. I'm sorry, till I was an instructor. Students kept saying SOHCAHTOA, and I'm like, what are you talking about? I never learned that. It's just a way to remember. Opposite, this is the opposite, and this is the hypotenuse. So S-O-H, I think this will help people remember it. Adjacent over hypotenuse. And then there's the flip versions of these, the cosecant. I'm not going to go into this in too much detail here. There's the secant, which is the flip version of cosine, and the cotangent, which is the flip version of tangent. Okay, so those are the definitions, and then you can use those. You can draw certain triangles, know certain values. What does this have to do with circles? Well, this only makes sense if you're strictly between 0 and 90 degrees. So what does it mean to go beyond 90 degrees? And we don't have to necessarily define what's beyond 90 degrees, but typically we do. And here's how we define it. So an important observation is the following, that if you draw a circle, and sorry, I'm doing a poor job here, but I'm trying to get through this piece, and you label this side X. It's on the x-axis, that makes sense. And you go up here, and you label that side Y. That makes sense, because it's how far you've gone on the y-axis. And then you draw this thing, which is the radius of the circle. You have a right triangle, because you went over and went straight up. And you have an angle. And so what can we say about the x and y coordinate? Well, we can say that sine, let me switch colors, because that's a bad color. We can say that sine of that angle would have to be opposite over hypotenuse, which means that y is equal to r sine of theta. And you're expected to know this going into a calculus course, but I find some students have forgotten this. And then cosine of theta is x over r. And I find most of the time, if you're forgetting something, it's not as hard as you think to get caught up, but you do have to recognize that you don't know something and immediately go ask. That's a key point of success. Okay, so somebody realized that in the first quadrant you get all these trig values. And so then somebody said, well, what if we do, what do we want it to mean if we go to this angle? Well, now it's no longer a right triangle. You can draw a right triangle over here, and there's going to be some similarities in the side lengths, except the x is going to be negative. But the question is, what is that angle? So at some point somebody's like, well, if somebody gives me 120 degrees, I'm just going to think of it as how far past 90 did I go? So that's 30 past 90. 90 plus 30 degrees. And then I'm going to use symmetry and look at the other side. So I'm going to go 30 less than 90. And you don't have to do any of this to do the calculation. I'm just explaining a little bit. And they said, really, we should treat 60 degrees like 120 degrees. Except we want the x to be the negative. And so then we define the following, basically, that cosine of 120 degrees is going to be the opposite of cosine of 60 degrees. And sine of 120 degrees is going to be the same as sine, and so on. So we just define them to be the same values moving around. But the key point of all that is x times the radius times cosine of theta is always going to be the x-coordinate. That's how we define cosine. So sine and cosine in circular motion are intimately tied together because that's how we define them past 90 degrees. So the point of all this is if you have something moving around a circle, and we have a few things. Because of this triangle in the first quadrant, we make a few conventions, which is this is going to be considered positive angles, and this is going to be considered negative angles. Does it have to be like that? No, but that's how it's standard, how it's defined, and how it's in your calculator. We call this angle 0. Okay, I think part of it is we like to start in the first quadrant. One could make the argument that maybe we should start up here, but we like to start on the x-axis. I don't know. But this is the standard form. If you don't like it, you can always look at your circle from a different perspective. You get to decide how to name your coordinate system. Okay, so the idea is this. If we've rotated for a while, and that's our angle theta, and we want to know this x-coordinate and this y-coordinate, we need one other bit of data, which is the r. And then we can say x equals r cosine of theta, y equals r sine of theta. So in a way, that's a definition. And then at some point in your background, you talk about a unit circle. And people talk about the unit circle because then r is just 1. So a few little things about that. If I pull up, stop this animation, pull up my website, you really can go anywhere on my website. But here's a unit circle review. It's really nice to have this memorized. That's just basically circular motion. That we say, okay, once we go past 90 degrees, we want the same value but opposite signs, and then we learn a few nice values to work from, relatively nice, and then from those we can get any of the other trig values. I have a different video on that. Okay. So in practical circular motion problems, this is all we're using right here. But we're varying r maybe or theta. So we switch gears now, if we want to do circular motion, to studying theta and studying r. So what we typically do is break it down as follows. We say, okay, if somebody wants to not start on the x-axis, they just need to tell us where they want to start. So we call that the starting angle. So let's say this is the starting angle of our circular motion. So we're going to start right here, and we'd like to call that time 0. And then we have this thing called angular speed, which is telling us how quickly the angle is changing. Is it 30 degrees per second? Well, then after 5 seconds, you multiply those two and you get 150 degrees. This is what we call omega or angular speed, and this is time. And that's just telling you how much of the angle you're adding on. So you'll add on to this. The amount you add on will be omega t. And when you're all said and done, this plus this is the angle. And then we're back to this same formula. So that's breaking it down a little more into the starting angle and the angular speed. But it's still the same formula. We're just now studying the angle and the way in which it moves. The radius can change too, and that's what happens in spirograph problems and in merry-go-round problems, and I'm going to play around with that. Typically in our precalculus class, we don't deal with problems where the radius changes. You could also have other formulas for theta. You could have it not be at constant speed. You could have it be accelerating. But that would involve just talking about what formula you want for theta. It wouldn't change what we're using. So that's it. That's circular motion. Now, to be good at this, it's good to know a few other things, like angular speed is the angle over time, which could be, degrees per second, or it could be, radians per, and you can pick whatever time you have, radians per minute. A very popular one is RPMs, which is revolutions per minute. In most calculus, we want to use radians. If you're using revolutions per minute, you have to convert. One revolution is the same as 2 pi radians, so you can write 2 pi radians. Basically multiply by 2 pi. So if it's 5 revolutions per minute, then I teach students to do the conversion. I say put radians here, the unit you want, put revolutions on the bottom, and then write an equivalent fraction. 2 pi radians is the same as 1 revolution, so this is the same as 10 pi radians. So often in practical problems, people often want revolutions per minute. It's easier to describe things. They can see the thing has revolved so many times a minute. But in practical, actually in the formulas, we typically want radians. Okay. Linear speed is how fast you're actually going, and that depends on where you are in the merry-go-round. If you're standing on the edge, you're going to be going much faster than if you're standing in the middle. And what I mean by faster is faster in terms of linear speed, speedometer speed. If you're at the end of a long propeller, you're going much faster than the beginning because you're going a further distance in the same amount of time. So we like to separate these two things, and there's 3 key formulas, and those formulas require we're thinking in terms of radians. The arc length formula requires radians, and these are just things about angles. So this requires really a course. These don't come up that much when you're doing circular motion, but I felt bad to not mention them. I did talk about this. And the connection between linear speed and angular speed is very vital. So if you're doing belt and wheel problems, and it requires you're in radians. So these would be helpful if you said, I want someone on the edge of the merry-go-round to be going 30 miles an hour. So that would be helpful because you could then say V is 30 miles per hour. And then figure out, based off of the radius, what the linear speed should be. And then you can fill that in. So the point of that is a bit more, knowing a little bit more about speed can give you better pictures and models. I'm going to finish by going back to those pictures. So in Desmos here, just a little preview of things to come. So I made it so, if you change the radius, that doesn't matter. You can see there's the formula, so I'll animate it. So there we have circular motion. This one's starting here. I could tweak some of these. So if we wanted to start at the top, we would just do pi over 2 plus pi over 2 plus. And now if we go back to the beginning, we start at the top. And that will have us go counterclockwise, and we'll complete a loop in however much time. If we want to complete the loop faster, we can change the angular speed. And now we're going faster. 2 radians per second are completed. So that's the tweaking of the model. If you want to go the other way, then you make this negative. So back to the beginning, and that takes us clockwise. Because we're subtracting, we're making the angle more negative. Okay. I am going to, in my spirograph video, I did this earlier today. I was drawing some spirographs with my niece, and one of the pictures we got looks sort of like this. I can tweak the pieces a little bit. There's a few spirographs if you ever played with those before. But this is all circular motion. It's actually two circles. So I'll derive this in a future video. I'll explain how I get this, but it really is not any more complicated than using this. It's just the radius is changing and you have two different, so it's basically adding these two pieces together. But here you go, you can watch it go. Let's take it back to time 0. So if you were to put your pencil in the spirograph, you have this bigger thing around it, and I'll do that in a separate video, and an inner gear, and you put your pencil right there, it will then follow, I might need to slow it down, in that inner gear, as that inner gear turns, and you get this. And if I make this a little smaller, so there's kind of the beginnings of it. But then if you keep going, it goes. And if you keep drawing, if you've ever played this, kind of fun. And as I was researching for that video, there's a lot of stuff done on spirographs. So none of this math will be new. But I just wanted to show you that you can make these pictures yourself, and all it requires is a basic understanding of r cosine of theta, r sine of theta. That's it. If you look in our precalculus course, this is one of my old second midterms, we do questions that involve belts and wheels like a bicycle, and that's where we use these facts about linear speed and angular speed. And the point of those questions is to get a better understanding of the differences between those. And we talk about how the fact that A and B are connected by a spoke, they'll have the same angular speed. It takes the same amount of time to do one revolution. And you can see I like to make a little table. You can see those are the same. It turns out that if you connect two things by a belt or a chain, they have the same linear speed. If a bug lands here or here, it's going the same speed. So those are the same. Using those two principles and these couple of formulas, you can do a lot of belt and wheel problems, and I plan to do a video on that later. I'll probably do something about this later too. And then we always have these exam questions that have to do with circular motion. Here's Harry and Ron. This was when I went through my Harry Potter phase. I had guinea pigs with these names. But anyways, I have Ron starts here. The radius is 60. He's going 0.02 radians per second. There's his formulas. And I say, where is he after 30 seconds? So this was not a hard question. But I remember students being mixed up by it. And then Harry goes the other way. So his angular speed is negative. I had to do a little bit of work to try to figure out so they get to the same spot. This one didn't require full circular motion. I just wanted to find an old exam question. So all of those exam questions, those students doing this in their pre-calculus courses, will help you as you get to trying to model circular motion, or even more when you get to 3D and you have circular motion in two of the variables. Viewed from above, this is just circular motion. And so a foundational understanding of circular motion is needed as you move through the calculus courses. And there's not a lot going on. It's really this formula right here. That's it. Everything else is trying to help us plug into that formula. So in future videos, I will do some case studies of some problems that I have found interesting over the years. They're just circular motion. I'll do one that involves working on a swing. It's the same formula. How the angle changes is really different, but it's the same formula. I'll have two people on a seesaw that are moving. That's circular motion. They're not going the full range of the circle, but it's circular motion. I'll have somebody on a merry-go-round. I'll have spirographs. There's just so many problems that just require this. And with a little bit of knowledge, you can make your own cool 3D visuals. I also took courses. I was a computer science major originally, so this helped me when I was trying to graph things. I know some computer programs will do that themselves, but a little bit of understanding goes a long way here. All right, hope you find that interesting, and I'll follow this up I'm about to start a new quarter, so I'll have less time, but I'll follow this up with some future videos about other examples of circular motion. Let me know if you find that interesting and helpful. Thank you.